Activity 9.12 is angles and polygons. We are going to come up with a general formula to find the sum of the interior angles in a polygon. We already proved the visual proof that the angles inside of a triangle add up to 180 degrees. There are three sides in a triangle. There's one triangle, and there's 180 degrees if you add up all three. We can draw a diagonal in a square or any quadrilateral, and we create two triangles. There are four sides in any quadrilateral. That means that if you add the interior angles, you do 2 times 180 because the left triangle and the right triangle each have sums that add up to 180 degrees. If we do this in a pentagon, and you don't have to draw all diagonals, and you don't want the diagonals to cross. So I like to pick a vertex and start from there to draw my diagonals. You have 5 sides, and now I have 1, 2, 3 triangles. That means that the sum inside a pentagon should be 3 times 180. You take out your calculator if you want and do 3 times 180, which is 540. It does not have to be a regular pentagon, by the way. This is a regular pentagon, any pentagon, and we can go back to the house we made with pattern blocks and add the 5 angles, see that that adds up to 540. For a hexagon, I fan out again, I can make 4 triangles, and I'm starting to see a nice pattern. And that equals 720 degrees. And then for 7, if I fan it out, I bet you it's going to make 5 triangles, 1, 2, 3, 4, 5. And then we will do 5 times 180. And 5 times 180 is 900 degrees. And that pattern would continue. It would continue for an octagon and so forth. So we just did up to 7 sides. So can you find a pattern? How do the number of sides and the number of triangles compare? Well, if I have 3 sides, I have 1 triangle, 4 sides, 2 triangles, 5 sides, 3 triangles. So it looks to me that the number of triangles is 2 less than the number of sides. Can I use that to write a general formula to find the sum of the interior angles of a polygon? Let n equal the number of sides. So if n is the number of sides, then n minus 2 is the number of triangles. So the sum of the interior angles would then be n minus 2 times 180 degrees. It's the number of triangles times 180 degrees because each triangle, the interior angles will add up to 180 degrees. So that works for all polygons. So n can be any number of sides. A regular polygon would be an equilateral triangle, a square, a regular pentagon. I've mentioned that before. It means all your sides and all of your angles, interior angles, are the same. There are 2 more types of angles, and that is a central angle and an exterior angle. So we've been talking about the interior angle. So if we think about the central angle, a full circle is 360 degrees. If I divide that by how many central angles I would have, and we can fan this one out from the center and see you have 1, 2, 3, 4, 5 in a pentagon, it would be m. That would give me the central angle. Okay, now for the exterior angle, let's think about that a little bit as well. So I'm going to take an extra piece of paper and show you some work. Just follow along. So right here, an exterior angle is where you extend the side of any polygon. So if you see right here, you see that the side is extended. That's the exterior angle. The exterior angle plus the interior angle make a straight line, which we know is 180 degrees. Now we just said the sum of the interior angles was n minus 2 times 180. If all interior angles are the same, I can divide that by n to get one of them. So that exterior angle is going to be 180 degrees minus the interior angle, which is 180 degrees minus. So the sum was n minus 2 times 180. I only want one of them, so I'm going to divide it by n. That would give me one of them. Okay, let's simplify this. This is a formula, but we would want to simplify it a bit. Let's distribute the 180 to get 180 n minus 360 all over n. Let's find a common denominator, which would be n. You can multiply 180 by n over n, because that's multiplying it by 1. And then we'll put it all over one common denominator of n. So I get 180 degrees n minus 180 degrees n. Now, minus a minus becomes a plus. 180 n minus 180 n is 0. And what I'm left with is 360 over n. So if I go back to my handout, the exterior angle and the central angle have exactly the same formula. And then the interior angle was my n minus 2 times 180 all over n. For this example, n would be 5, but we can do it with any example. Okay, so the sum of the interior angles, when I fill this out, I can use the previous page. Triangle is 180. Quadrilateral is 360. Pentagon was 540. Hexagon was 720. Heptagon was 900. To keep adding 180. At the bottom here, our formula was n minus 2 times 180. Now, the next part is for regular polygons only. That means all the sides and all the angles are the same. So if I want the measure of each interior angle, also called the vertex angle, we know that that is going to be the sum divided by the number of sides. So this would be 60. 360 divided by 4 is 90. 540 divided by 5 is 108. 720 divided by 6 is 120. 900 divided by 7. Oh, it's not nice. It's 128.57. Okay. The exterior angle is going to be 360 degrees divided by the number of sides, by n. This would be 120. We know central angle is the same. And we get 90. It's 72. So I'm taking 360 and dividing it by n. This should be 60. And I'm assuming when we divide by 7, it's not going to be nice. It is 51.43 if I round to 2 decimal places. So you go ahead and fill out for 8, 9, and 10. We know that this is n minus 2 times 180 over n. This was 360 over n, and this is 360 over n. So make sure to fill out the last two tables. Two rows, not two tables. Three rows. I'll get it right one of these days.